Next up, we have Oleg Stepanyuk, who is going to talk to us about advanced multi-instrument image processing and feature tracking for remote CME characterization and convolutional neural network.
Yeah, pretty long, I believe. So, good afternoon. Thanks for introducing me, but I'll repeat. My name is Oleg Stepanyuk, and let me present today some of the work we are doing here in Sofia at the Institute of Astronomy of Bulgarian Academy of Sciences. So let's talk a little bit more on image and data processing. Apologize. So, I believe a lot have been said these 2 days of the conference on various aspects of CME-related research. And our goal was to try to present a general method for tracking of various heliospheric and solar eruptive phenomena, and if we are lucky enough, the software. Because actually, last years we have indeed unprecedented remote and in situ solar observation instruments, so we have quite a lot of data, and the idea is that these data, provided it's handled properly, could really help to constrain existing theories. So, main challenges here, obviously, is so one can approach this from the point of data-driven. That's what was mostly this conference is devoted is about, and also obviously we have an algorithmic approach, which is known for its complexity, very complex image processing chains, and in terms of CNNs, the first question that we have is availability of the training sets, quality of the training sets, whether we're gonna introduce those ground truth images biases into our models. So, and here we present hybrid, both algorithmic and data-driven method for detecting and tracking of various solar and heliospheric phenomena. So first we'll talk a little bit algorithmic, then we're gonna move into UNet and data-driven and more common stuff. So in human words, the idea was to have some tool or some method that would help us to create training sets and masks automatically or semi-automatically, so that the code would work in pipelines, or at least with a little bit of a human intervention. The core of the method is A2A wavelet decomposition. In human words, that means that each decomposition level or scale represents its own detailization level. So higher the scale, more the details of the larger size are highlighted, while smaller details are omitted. Basically, the idea comes out of the Hilbert space decomposition theorem that states that any Hilbert space could be decomposed into the subset of orthogonal spaces. Well, in our cases, these are wavelet subspaces. So why are we doing this mumbo jumbo? Because there are two actually approaches. One is pretty simple approach when you can take the higher scale, like wavelet coefficient 5 you see here, which basically would represent very rough shapes and details, and you could use it as your mask. Or you could go in with a more intelligent approach and try to derive from the first principles the criteria for the object on your image, which essentially would depend on the maximum wavelet coefficients on the different scales. So we developed the code, and single cadence step or time step processing routine goes as follows. Initially, first a little remark. What we are talking now for AAA is DO images. Initially, base difference or running difference images are obtained. After that, we apply a certain thresholding because we understand that features physically interesting of our interest, like for instance, the shock wave. It's a pretty dim, the feature that exists in a very narrow part of the extremely wide dynamic range image. So it makes sense to pre-select manually if you, according to your knowledge and intuition, because okay, we know where, roughly speaking, in which part of the image these features exist. Then images are decomposed with A3 wavelet decomposition technique. And then either reference masks, either objects criteria are applied, certain filtering techniques and pasteurization median filter could be also applied. And what do we have actually on the output? The left column of this image, we see base difference images. On the right, on the next column, the second column, we see object masks. So now going a little bit further, one can think of it as one elementary kind of, sorry for being a little bit scholastic, one element of the training set. So on the left part, you have your actual data. The second column is your ground truth. And that effectively allows to process numerous events, well, pretty rapidly, because with Yafta wave, for instance, or where it could take for a couple of time frames, it could take a couple of days. So it's really, it wasn't that simple. So this work was published in journal Space Weather and Space Climate the last year. Yeah, by the way, about contrast. We had, I believe, with Manuel and some other people had lots of actually discussions about the contrast. Contours of the features were obtained by convolving images with Sobel-Feldman operator. Well, basically, you can think about it as the gradient, but it works better for the purpose, so to say. It's kind of visually represents the results better. So, how much time do we have? Huh? 5 more minutes, or 10 more minutes, sorry. 10 more minutes, yeah? Okay, great. So here we present some examples of the tracking separately of CBF and the filament for the event that took place 11th of May 2011 on the upper part of the image. So, well, essentially, since from the point of image processing, it's essentially very different parts. So obviously, it's bending. It's two separate setups. And also, I have to say here that we have to process on-disk features and on-lip features again separately, because from the point of statistical distribution intensities, it's like totally different parts. On the bottom part of the slide, we see gigantic filament, capturing and tracking of the bigger filament. Oh, sorry. Here present series of a few more events just to illustrate the evolution, how the event evolves from. So on here we have different, I don't know, like a few minutes. A few words. So the method was also tested, but though with significantly different setups for K-core, LASCO C2 and C3 images. So here we have a continuous development of the event. First we start with SDOIA, then it goes K-core, LASCO up to I think 25 or 30 solar radii. So okay, and one can understand that that's all the training data, because now it goes more kind of traditionally and interesting, well, at least for traditional for this auditorium. Okay, I'll skip the UNET discussion. I think it was enough of that. Another one, okay, is about training and training data. Another important aspect is data augmentation. So basically it's how we are faking the data scientifically, trying to increase the size of the training set, but our fakes must obviously present something that could exist in the reality. So we must not kind of represent something unreal. So the most simple case is geometrical data rotation, although here one would have challenges. For instance, on the left part of the slide we have CBF event. On the left part it's, one image down, it's rotated, and you have those things with angles, so these spaces are still to be filled with the background noise. And a little bit more complex thing is data augmentation in terms of intensity. So in that case, the feature mask is applied to the raw data, and only this part, so effectively the part of the image which represents the feature of interest, could be little bit shifted within the dynamic range, or the intensities could be changed in terms of sigma units, 0.5, 0.6, well, so that, yeah. So, some results, 5 minutes overall, or 5 minutes to talk? 5 minutes and then 5 minutes, great. So here I present some results of our CNN code trained on both on disk and on limb events. So on the top we have base difference images. The second row is the ground truth, the control masks that are coming from the wave track. The bottom row is unit produced masks. So although the data is a little bit more noisy, and this is something I believe we discussed yesterday, so that whatever you do with UNet, in a way it's still prone towards first capturing different intensity levels. So these noises are effectively within the same intensity range as the wave itself. But in a way, it's even kind of better. Sometimes better reproduces the feature, although there is still space for improvement. Well, only here perhaps we're a little bit over with technology, and maybe some room for real science and physics appears, because at that point we can do lots of interesting things. Correlation tracking, for instance, here we show correlation tracking. Maybe better to show this one, at least it's a little bit better seen when we can see plane of the sky speeds performed with Fourier correlation tracking. For instance, well, now I'll be a little bit speculative. For instance, you could rotate those masks, which I'm already trying to do, and for instance, try to compare velocities, Alvan velocities. You could look what's happening on the magnetogram. So the main message here is that better shapes and better velocities coming from the data means finally more room for better science, so to say. That's what we are trying to do. And on another side, overcoming this bottleneck of the training sets. And one important thing, what I'm showing here is specifically was trained on a pretty small training set. So that is something that was derived out of just five events with all data augmentation. Why? Because, well, actually, that all stuff gonna be in the paper. They're gonna be a little bit more, but still, okay, it's not afterwave or not aware processing events with wave track. It's still somewhat demanding. So sometimes it goes smooth, sometimes not that much. Sometimes you could get really a little bit noisy mask. So, and you obviously don't want to have such data to introduce your ground truth bias into the model. And final goal is to have more or less black box solution working at least for a few instruments that would be able to capture shapes and velocities of the various heliospheric phenomena. Well, sorry, it's too broad. I would say eruptive features, maybe. Yeah. So thank you. I think that's all for now.
Great stuff, thank you. Have we any questions here in the room? Yeah.
Thank you, Oleg. A quick question has to do with your result of taking the speed, the range of speeds of the CMEs it comes out, and you have a color bar in there. What do you need this information for? How do you see this information being useful? What we typically have is the plane of the sky speed, for the entire structure of the CME, and we say the near sun speed of the CME is such and so. If you have a spectrum of velocities, what kind of physical gains could you have by this result? I mean, it's a lot more information that we used to have, so we ought to be able to put it to a good purpose. How could we use it?
Well, I could think of obviously various applications. For instance, one of which I've mentioned, for instance, let's imagine that we try to reconstruct the 3D surface, look at the velocities on the how to say on the contours, for instance, and then okay, you could try to compare it with Alvan speed, for instance, or and yeah, so basically from that you can really try to derive lots of physics and say something about the nature of event. Well, particularly if you would have magnetograms, because okay, generally speaking, if MHD is, let's say, Navier-Stokes plus Maxwell equations, and in half of the equations you have velocity included. So I would imagine that quite wide applications are possible within kind of.
You might be able to resolve the shock properties a little bit better than having a single velocity, which would allow you to tell, okay, there's going to be a shock or not. You'll be able to do that, and that's important.
Well, I believe I mentioned it. By comparison, you mean with Alvan speed, how your speed is? Yes, that's what was meant. Yeah.
Yes. The structure of the shock as it comes out of the sun.
Oh yes.
You see you're resolving the shock in a way, rather than saying there will be a shock or there will not be a shock. You're able to resolve the shock, which parts of it are going to be more pronounced and which part are not.
Yes.
How corrugated the structure is, how much of a coherent structure it is, things like that.
Okay.
Have we any other? Oh, comment in the back.
Yes, maybe just to add, yeah, so we're definitely interested in learning about the overexpansion, for example, which we know is related to, or we suspect strongly is related to the production of SEPs, very low in the corona. And furthermore, these don't have to be shocks. They can be compressive waves. The solar energetic particles see differently in a way because of their huge gyro radii. So they can be compressive waves. We don't impose such a strong assumption. But yeah, interaction with the corona, how the feature, the UV wave or coronal bright front is expanding in different directions, and how it interacts with the streamer structures, for example. All those things can be inferred from such correlations. Thank you.
Brilliant. Anything else here in the room? And I don't see anything else online, so I suggest we take our extra 2 minutes and take coffee early. All right, everybody, please be back here for 4:20. Thank you.
Thank you.